One of the cool ways that we can solve a problem like this is we can use derivatives and the second derivative test to actually test if our graph is a minimum or a maximum. But in the end, we will be using calculus to actually find the minimum and maximum points. So you may recognize a question like this, as if I've covered one of these and a bunch of these actually from my Unit 1 video on quadratic functions. All we're doing here is we're trying to find the dimensions which actually will maximize the area of this garden. So our perimeter, since our perimeter is going to be, or add up to 600, and since we have 4 W's here, we're going to have 4W plus 2 length is going to give us that 600 meters of fencing all around. Now, we need to make an equation for area. So the area of a rectangle is length times width, and we want to have a max. We want to find the maximized area. So in order to do that, we actually have to isolate for one of our variables in our first perimeter equation. So we started off with 600 equals 4W plus 2L. I want to isolate for the easier variable to isolate here for. So what I'm going to isolate is 2L. So we're going to 2L is equal to negative 4W plus 600. Divide both sides by 2, and you get negative 2W plus 300. So now from there, we can actually plug in our expression for length into our length times width area equation, since we're looking for the area. Now, once you plug that in, you're going to get negative 2W plus 300 times W is equal to the maximum point. All you have to do is you have to distribute that W onto both of our variables here, and you're going to get something that looks like this. Now, as for solving this, this is where the calculus part comes in. We're going to take the derivative of this function. So what is the derivative? We're going to do something called power rule to take the derivative. So x to the n equals n to the x n minus 1. So you'll see what this actually means, right? Like, what the heck is that? So let's do this. So we have negative 2, and we have this to raise to the power of 2. So we're going to drop down this 2 as it's done in our exponent or our power rule. So we're going to have 2 times 2. And then our variable, we're going to subtract 1 from the exponent. So W to the 1, since 2 times 1, or 2 minus 1 is going to be 1. So this gives us negative 4W is our derivative of negative 2W squared. Now, in terms of this 300 over here, we're going to do the same thing. So this is W raised to the first power. So what we're going to do is we're going to move this down here, and you're going to get plus 300 times 1, and then you're going to subtract 1 from this power. You're going to notice you're going to get W to the 0, which is also equal to 1. So we're going to get negative 4W plus 300 is our derivative of this original equation. Now, where this actually gets cool is when you set your derivative equal to 0, that is a maximum or minimum point. So let's set our derivative equal to 0. So we have negative 4 plus 300 is equal to 0. You're going to solve for W here, and you're going to get W is equal to 75 meters. This is one of the dimensions that will give you the maximum area, and we've done it really quick. We just took the derivative of our function, and we've done it in 2 steps instead of solving and doing all the work that comes with that. However, you probably may be wondering, what may happen when you have the derivative of a constant? Like, what is the derivative of, like, 300, for example, if we just had 300 at the end, or plus 300, right? The derivative of any constant is going to be 0, so you don't have to worry about that. It just cancels out. Now that we've found our first dimension, we can go back to our original, or one of our first equations that will come in handy. So we got length is equal to negative 2W plus 300. All we have to do here is we have to plug in our maximized W, which is 75, plus 300, and this will give us our length. You're going to get your length equal to 150 meters. Done and easy. That is how you use derivatives to find the dimensions which maximize your area. So, the way we can actually test and use our second derivative test is if we do our second derivative test, which we're going to do over here. So all we're doing is we're taking the derivative of our derivative here. So we got negative 4w plus 300. Now let's take the derivative of this. So the way we do that is we're going to use power rule once again. So negative 4, and w is raised to the first power. So we're going to bring down that first power here and subtract 1 from the exponent. You get w to the 0, which is just 1. So you get negative 4 as your derivative of negative 4w. Now for 300, remember that derivative of any constant is going to be 0. So we're going to add 0. So our derivative of our second derivative is going to be negative 4. So what does the second derivative test actually tell us? The second derivative shows us whether this point is a maximum or a minimum. So if our second derivative is greater than 0, then it is concave up, meaning that it'll open up and create a minimum point. Notice how our second derivative here is negative. That's because we have a maximum point, which is going to be when it's less than 0, meaning it's concave down. We have a concave down, meaning our parabola will open downwards and create a maximum point. This is how you can use the second derivative test and derivatives of functions to find the maximum area and do optimization word problems.